Section 4.5, page 3, but let's just do example 2 only first. Reading the question, a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of this base is twice the width. Material for the base costs $15 per square meter. Material for the sides costs $9 per square meter. Find the cost of materials for the cheapest such container, round to the nearest cent, meaning the hundredths place. Okay, the reason the base possibly costs more than the sides is it may have to be a little bit stronger to hold whatever is being carried, but the sides only need to be strong enough so that they don't break open. So as I'm described this cubic volumed rectangular shape, I've gone ahead and drawn a cube, which normally we have width, length, and height, but we're told that the length is twice the width. So this length, since it's twice the width, I just changed it to 2W. But let's go ahead and get into solving this. Our goal is to find the cost of materials for the cheapest such container. So what cost is the cheapest? And I've got these various dollar amounts. So we know that the base is $15 per square meter. So my base consists of W times 2W, which is basically 2W squared at $15 a square foot. I have 30W squared for my cost. Now, in terms of the sides, they're $9 each. But here's where you've got to be careful. The front, as you can see, is width times height, but I also have a back. So width times height twice is 2HW. I have the right side, so let's move this H over here. I need to multiply H and 2W, but I also have that left side that you can't see. So I have two of these. So 2HW twice is 4HW. So I've got the front and the back, the left and the right, and at $9 each, well, actually these are the same dimension, so let's go ahead and add those. I get 54 height times width, not homework. So the total cost is the base, which we found to be 30W squared, and the sides, which we found to be 54 HW, and this is what I want to minimize. I want it to be as cheap as possible, but I've got a W and a WH over here, so I can't necessarily take the derivative yet. There's always that other piece of information, the constraint, that's going to help you. We know the volume is 10 cubic meters. The volume, length times width times height, needs to be 10. But remember, I don't actually have a length. I have 2W where that is. So I've got 2W squared equals a number times H, sorry. Since H is not squared, let's go ahead and solve for H. We knew we had to solve for one variable, so dividing both sides by 2W squared is easiest, and then I went ahead and simplified. So I can go back to the function I need to take a derivative of, and where the H was, I can go ahead and put 5 over W squared, which will allow me to simplify one of my W's. And I know I'm going to take a derivative in a minute, so I went ahead and moved the W to the numerator by using a negative exponent and multiplying 5 and 54. I want to optimize this function that now is in one variable. I do this by finding the critical values. So taking the derivative of 30W squared, taking the derivative of 270W to the negative 1, and setting it equal to 0. So adding the negative term to the right, cross multiplying, dividing both sides by 60, and then needing to take a cubed root of both sides. Now I lucked out and I got a decimal that terminated on the left. Otherwise I would have left it as the fraction, 270 over 60 before I took the cubed root. Don't forget, you can take the cubed root by taking the 1/3 power of both sides. And when I took the 1/3 power of 4.5, I got 1.6509, etc. Even though I only want to round to the nearest cent, I'm going to go ahead and maybe do that now. But if it was rounded up or down, I don't know, I might leave a few more digits. I need to verify that this minimizes the cost. So I'm going to go ahead and take this first derivative and take the derivative of that. 30W, sorry, we already took the derivative. I apologize. The derivative's down here. 60W has a derivative of just 60. And when I had that negative 270 to the negative 2, I'm going to get positive 540 to the negative cubed, but I'm going to bring that to the denominator. When I plug my number in, all I care about is I got a positive. That means it's concave up, and I can see that concave up has a minimum. Now to answer what was asked. I was asked to find the cost that would be the cheapest. I don't know what the height is, I only know what the width. So you could find the width, or instead, look at what we did at the end of part 3. At the end of part 3, the function I used did not have h, so I could go ahead and just plug my W of $1.65, sorry for meters, into that portion, and I end up getting this answer, and it was just cubic meters. We just had dollars per square meter, so it's not like it was thousands of dollars. My units are just dollars. So I can build that box for $245.31 with the cheapest cost.